Hello, we're going to be doing power analysis, and we're going to use practice problem 11.1 on page 289 in the text. I'm not going to read out the whole question, but here are all of the relevant stuff that I pulled out from the wordy paragraph that is the question. We have 14 people in our study, or 14 samples. The alpha value that we pre-decided was 0.05, and it's two-tailed, so we're not looking for if the probability is greater than or less than. We're looking just if it's different, right? So there's some implications there. And then it says do a power analysis to find the probability that we would be able to find an effect if it was either 0.8 or 0.2. So they have to give us 2 because it's two-tailed, right? It could be really high, a lot higher than the 0.5, or it could be a lot lower than the 0.5. And the 0.5 is if chance alone was acting for it, if the null was actually true. So step 1 is we figure out our basically our type 1 error rate. If the null was true, so I'm going to set this to n of 14 and p equals 0.5. If the null was true, what's the probability of us finding a significant effect? So I'm just going to copy all of that stuff down there. Alright, and I'm going to say what's the sum of all of this stuff. Before I hit enter, what do you think the sum would be of all the different probabilities? It better be 1, right? Or at least it better be really close to 1. Perfect. Okay, it's basically 1. It's not exactly 1 because this simulator only gives us out to 3 decimals. This 000 is not actually 0. It's actually 0.000, maybe 0.00001 or something like that. Something really small, but not exactly 0. So it's fine. So my job is to figure out what are all the possible outcomes. You know, what is that p-value? That p-value is the chance of finding this result or more extreme, okay? And so we're talking cumulative percent. So let's say we found all 14 was true. Or say we found our p-real was like 1 and we found the 2 n's. So like what we're doing is we're trying to find where our critical zones are, right? We're trying to find out exactly where our critical zones are. So if we add up we're going to start from the outside and work our way in. So let me just drag this sum over here. Right, we're still nowhere close to our 0.05 alpha rate. So let's go a little bit in. Right, I could just be starting from one extreme and working my way in, and then doubling it, which is what we do sometimes in class, which works fine for the symmetrical distribution, but it won't work for the step 2. So I'm just going to do it this way. Yeah, okay, so we're still well within our 0.05 alpha range. So we're going to go one more in. What happens if we get 12 out of 14 heads? Yeah, we're still close. Let's keep going. 0.05, okay, never mind. We've now are no longer within our critical zones. We're above 0.5, so I'm going to go back. And so it looks like we would be able to find a significant difference if we got 2 or less, or 12 or more, okay? Alright, so that's our step 1. This is actually this experiment's type 1 error rate. Yep, 0.014. That's our type 1 error rate for this specific experiment. If the null was true, which is why that's here, what's the chance that we find a significant effect? Okay. Now, what is step 2? Step 2 says we plug in our expected, or the p-real values. It depends when you're doing the power analysis. So, and then do the same thing. So if I'm going to change this to 0.8, I'm going to copy and paste. Alright, so you see how these are different. See how moving this probability basically just changed where the mean is, and then it kind of messed with the distribution because the whole distribution is kind of scrunched on this right side. Alright, so if I just take the bottom 3 values and the top 3 values, because again this is a two-tailed test, and I want to find the sum of all of these guys. 0.44. So what is this? 0.44? This is our power. We just calculated power. We have a 44.8% chance to find a significant effect if there actually is one. Yep. And what can we do with power? Well, what is beta? Beta is 1 minus power. So I can say my beta is equals to 1 minus 0.448, which is 0.552. So that is our beta rate. That is our type 2 error rate. So even if the alternative is true, if the probability is actually 0.8, we have a 55% chance to not detect a significant difference, which is terrible. These are pretty terrible numbers. What these normally are, what we try to get them to normally is we want an 80% power, so 80% of the time we run this study, if the effect is actually there, we'd be able to detect it. That's what power is. And which would make this beta be around 0.2. There'd only be like a 20% chance that we'd miss that signal if it actually was there. Yeah, okay. So I only did this for 0.08 or 0.8 real, p real of 0.8. But if we also do it for p2, what do you think it would be? It's going to be the exact same thing. So the top 3 and the bottom 3, if I drag all that over, this is the sum. Yeah, this is the sum of all of that stuff. So it's the exact same thing. Say 0, 0, 0, 0.044. Yeah, these are the same thing. It's just swapped, right? This distribution is the exact same as distribution, just on the other side. And since it's a two-tailed test, it doesn't matter because we have to take stuff from both sides anyways. If it was a one-tailed test, it might actually matter. It definitely would matter. All right. So what did we do? We calculated our type 1 error rate, which is this part. We calculated our power, which was this part. We calculated our beta, which was this part. And we basically described the probability of correct rejection. I'm not going to type it out, but yeah, correct rejection, all the 4 possible outcomes.